Just a couple of words before beginning. As usual, if you have any question during the presentation, write them on the chat, and we are going to read at the end of the presentation. So now I will give the word to Adam.
Thank you, Gianluca. So first, I'm going to introduce you to network motifs, temporal network motifs, egocentric temporal motifs, and an application we did, and a possible future direction we can take, especially with a focus on the biological field. And I will try to be like fast on the theoretical part and so forth. So networks, I think many of you know what a network is. Basically, is a pair of sets, so a set of nodes and a set of edges. And we have relationships among these edges. What we can model with these graphs? Well, we can model social networks like the social network we use, real social network like interaction among people. We can model molecules. They can also be seen as graphs. We can even model sentences because we can build, starting from a sentences, the subject, the adjective, and so on and so forth. And we can build a graph. And we can even think to images as a graph, because we can apply a technique like superpixel and convert an image in a graph signal or something like that. Basically, everything in the world is a graph. So how can we study networks? Well, there is, first, we can study the topology of networks, like the degree, the clustering coefficient, assortativity, connectivity. There is a lot of stuff. On the other hand, we can run simulation on the network, like try what happened if we simulate an epidemics in a network, or if we see, I don't know, what happened in terms of L0 or infected people, and so on and so forth. Another way to study networks is to study the motifs of a networks. What is a motifs? A motifs is a substructure of a network that appear significantly more often compared to random graph. So in order to better explain this, I think it's easy to see the procedure to extract this. So given an input network like this one, we would like to count all the possible substructure that we find in the input network. And we can generate then, once we have counted all the subgraph, we can generate a lot of similar network to the input one, count again, and then what we do, we apply a statistical test that basically is overrepresented. We look for those structures that are overrepresented, that have a minimum deviation and a minimum frequency, and those structures can be called motifs. Okay. So to summarize, we have a network. We extract substructures. We evaluate which one of those substructures are significant for the real network. But there is a problem. So here I wrote count all possible substructure in the generated network. Well, this is really expensive because just try to think a little bit. So suppose we have 3 nodes. How many substructure with connected substructure we have with 3 nodes? 2 subgraphs. That is, okay, feasible and easy. If we have 4 nodes, we will have like something like 6 subgraphs. If we have 5 nodes, 21. And if we have 10 nodes, the number of subgraphs is really, really huge. So this part is really computationally expensive. Even if we are able to count once, so in this phase here, then we have to count all these substructure in the null models, and it's really expensive. So, and this is a problem, okay? Moreover, sometimes, I mean, many times, networks are not enough to represent real-world scenarios. For instance, Interaction can change over time. Images can be videos, or traffic on the roads. It changes depending on the hour and so on and so forth. So temporal networks solve this problem. What I mean for temporal networks, basically the same structure. So again, nodes and edges connected, but they change over time. What does it mean? For instance, edges can change. If we think to interaction among people, right now I'm talking with one person, and I don't know, 10 minutes later, I'm going to talk with someone else. So edges change during the time, or nodes. Just think to people that join a new social network. So they enter in a specific time, or attributes. For instance, if I have an edge that connects me to a friend of mine, we can become enemy, for instance, and the arch will be enemy instead of friends. Of course, what we can do, we can study the topology and the simulation, I mean, in terms of dynamics. And of course, we also have temporal motifs. And basically, what happened? It happened that we have this temporal network that is a network as we are used to see, but also we have the time in which the interaction happened in this case. And Paranjape et al. Proposed this method based on dynamic programming to count motifs and how a motifs looks like. Basically, it's a simple motifs, but we have also order on the edges. So, cool. It seems that the problem is solved. But just try to reason a little bit on how many of those substructure do we have. So, for instance, those are all the possible static motifs with 4 nodes. If we add the order on the edges, well, we could have, if we try to open the first one, then we have that this simple structure became a tree structure. If we try to enumerate the edges of this structure, became this one. What does it mean? It means that the complexity is really, the number of structure with enumeration is really high. And what does it mean? It means that we require a lot of time to compare similarities. I mean, to decide if they are if the two motifs are the same. And this is a even big problem if the size of the graph grow, if the size of the substructure grow. Like, for instance, those graphs are identical. The only difference is that you have a different naming of labels, but the graphs are identical. And so we have this huge problem. So before we said that normal motifs has the problem of counting of all possible structure, and it is expensive. Here we are adding another layer of complexity, and so it becomes much more complex. So how can we solve this problem? Well, we propose this method called Egocentric Temporal Motifs that allow you to compute in a really fast manner if two substructures are identical or not. Okay, let's start. Suppose we have a temporal graph like this one. So we know that the edge from A and D goes from time 1 to time 3, or this edge from C to A only at time 1. Okay. What we can do, we can see this temporal graph as an array of static graphs. For instance, we can just take the time 1, we take the same structure and only those edges that appear in time 1, time 2, time 3, 4, and so on and so forth. In this way, we have an array, an ordered array of static graphs. What we can do, I mean, what we propose given a number k, so a number of layers we would like to have, we can see this graph, this ordered sequence of static graphs as connected. I mean, what I mean is that the node D is still D even the time +1. So we can connect in some sense these edges with this dashed line. We can choose a one node. For instance, I chose the E node. We can call it ego. What next? We extract from the ego node. So we decided for the ego node. We decided for a key equal to true, but they are parameters of the algorithm. And what we can do, we can extract the first order neighborhood. What does it mean? It means that from E, we take the neighborhood at hop 1. Well, it means that in this layer, we are taking E and the first neighbor. In this second layer, we take E and B because they are connected to E, but they are, for instance, D is not connected, so we will not take it. Once we do this, we have this structure here. Okay, we call it egocentric temporal neighborhood, but who cares? It's just a okay, once we have this structure, we still have the problem to compare to structure that it's still complex to do. So what we can do, we can say, okay, just try to have a node encoding. So for each node, we are trying to convert them in a unique manner. Okay, let's try. So, and we thought to this node encoding. So for instance, the node A appears at time 1, at time 0, time 1, and time 2. So it is represented as 1, 1, 1. Then we have the node B does not appear at time 0, it appears at time 1 and 2. So we have 0, 1, 1. And so now we have a node encoding. What we do, basically, we sort the node encoding in, so we put the, we sort the node encoding and we concatenate it. So at the end of the day, what we have a string that represents the structure. We have a method that allows you to convert this structure in a string, and we can do the vice versa to get back to the original structure. Of course, we do not have the ego information because the ego, we know it's always connected for all the k times. Okay, so in short, what we propose, we show this Etienne, this little substructure. We show how to compute this signature, and finally, right now we have a fast way to compare substructure if two substructures are identical. So, for instance, we have these two Etienne. We compute the Etiennes, and in order to say, are those identical? Indeed, they are. We have just to compare those strings. And we solved this problem in a really fast manner. So, in the previous procedure, this computation here, now it's fast. And what allows us to do? Well, now that we have built this strategy to have substructure and use a substructure to compute statistics on networks, how can we use it? Well, the first, the idea that we applied in the proposed work is the compute distances. So what we did, basically, we are just computing, given in input two graphs, so temporal graphs, G1 and G2. We would like to know how much they are distant, okay? Here, what we are doing basically is a cosine similarity among this stuff, and what this does. Basically, m of G1 is given a set of Etienne, so the egocentric temporal motifs. We count them, so we report the count. And so here, this one is a vector containing the count of Etienne. And with this, we can compute a distance between two graphs. So just to show you some simple results, we took this 7 data sets representing face-to-face interaction in a real-world scenario, like an hospital, workplace, and so on and so forth. And we use this algorithm to compute distances. And interestingly, this reflects what we would expect in real life. So for instance, here I'm showing that the workplace and the hospital have interaction that they are quite similar. In fact, both of them are workplaces in some sense. It's the same for high schools, so we can see that the distance is really small compared to other stuff, and it makes sense, I mean, for us. And also for the primary school as a typology of interaction that is totally different from both the workplaces, the high school, and even the university. And if we have a look to the type of interaction in a university, we have that it is quite similar to the interaction that people has in a high school is quite similar in a university, are quite similar to those in a high school, and a little bit far from a workplace, and a lot of far from a primary school. And it makes quite sense in terms of what we would like to expect. So other future direction, and here I'm not an expert on biology. I just try to think to application that I can have in biology, but those are, I do not have any kind of experiment of this. I just think it could be interesting. So first of all, what about biological neurons? For instance, in this data set, what they do, they collect the amygdala neuron activation when when the two individuals, they show images of, new images or images that they already saw. And they study the activation of the biological neurons. And this data for us are temporal network. One question is, what happens if we try to study biological, the network, this network with egocentric temporal motifs? Does it make sense to have an egocentric perspective? I don't know. I mean, I have no idea, but I think it could be interesting. Another idea could be to study the proteome, so the interaction among protein, and is it still temporal? So we can study what happened when, if we introduce the time dimension. It's the same for the interactome, so the molecular interaction. We can study, of course, epidemics. We can study the aging, so how the genes became old, how they change over time. We can also study metabolic network, and everything that can be seen as a temporal graph maybe can be studied with this technique. Yeah, that's almost. So in brief, we show the importance of temporal networks in the real world scenario. We show motifs in temporal networks. We propose these egocentric temporal motifs, a fast way to mine it, and finally, possible applications. And that's it. Thanks. Do you have any question?
First of all. Thank you for your interesting talk. I have 3 questions, if I can. Can you please go to slide 59? Yeah, here, exactly. So here, my first question is here. When you said that high school and university and yes, you said high school and university have similar interactions. And because in the previous slide it was written EMB, I immediately went to the previous one when you were showing because yes, here.
Yeah.
It immediately took me back to embedding, semantically embedding the concept. And when you showed the interactions and the fact that you said it has similar interactions, my first question is that, what do you refer to as interactions?
Okay, well.
So the relation between the other nodes.
Yeah, well, I did, thank you for the question. I did not spend too much time on explaining the data set. So basically, this social pattern data has been collected with this instrument, with this device, where people were asked to wear this device during the day, and every 20 seconds, I think, the device collect the interaction, the face-to-face interaction that I'm having. So basically, the data set is a temporal graph showing the interaction I have every 20 seconds. So for instance, if we were wearing this device, the data collected will be me and you talking together for, I don't know, 1 minute. And this is the kind of data we collected. And for interaction, we meant this fact here. So
I see. Because the way it is presented in this table, it seems that it is a very good idea to also semantically represent these places with respect to interactions, which can be inferred the similarity between them in other domains.
In fact, I skipped it because I mean, it would require too much time.
Right.
But what we also tried, instead of using all the motifs mined, we show that we can achieve the same results only using 3 motifs. So what does it? It means that only 3 of those, only the distribution of 3 of those, not these 1 others, can represent this kind of social context.
I understand. And the last 2 questions would be on slide 53.
Which one?
53. Yes, here. So here, from what I understand, correct me if I'm wrong, for this concept in total, we have this assumption that relations do not have a characteristics, because they can happen between each of 2 nodes, right?
Yeah,
Which
you're right. I mean, this kind of work, this work with graphs without attribute on edges.
Yes.
But we already have an extension of this mechanism that allow you to incorporate node attributes. So for instance, suppose that this one is a doctor and this one is a patient, for instance. You can encode this in this signature, and I'm sure you can, I mean, we didn't thought about it, but we think there is the possibility to even encode this typology of interaction, like enemy.
I see. No, because in many of the graphs, certain relationships cannot occur between certain nodes, you know?
Okay. Yeah,
so many reoccurrence and repositioning would not take place. And my last question is that, so because the examples you showed gave me this idea that all the nodes that are going to reoccur between different repositioning are already observed, right? Can it happen that in an example, in another graph subset, we have like few new nodes that have not been seen previously?
Can you repeat the question, sorry?
Can you please go back to the slides when you were showing? Yes, here is awesome. So can it happen that at the third graph subset we have a node, I don't know, a node epsilon that we have not seen it in any other ones?
Yeah. For instance, for instance, suppose that here the node B is not connected to the graph.
Yeah.
Suppose that this node does exist, but it starts existing at this time.
Oh, I see. So it's not only the occurrence of relations between nodes, but also appearance of new nodes.
Yeah.
Okay, thank you.
Are there other questions?
We have a question in the chat from Paolo. He asks, have you considered using this method to analyze the dependency structure, sample graph, the primal graph of logical formulas or other combinatorial problems? This could be used to find the most effective heuristics. Of course, I'm not talking about temporal graph.
Okay. Thank you for the observation. No, we didn't explore this direction, but we will definitely have a look. Thank you, Paolo.
Any other question? Yeah.
Well, first of all, thank you for the nice talk. My question is, can you deal with the case where sometimes with mistakes? I mean, I suppose at the high level, my question is how robust is this technique to mistakes, measurement mistakes? So sometimes you don't know that a node is there. Sometimes you don't know that an edge is there because the sensor somehow screwed up. What happens and how do you deal with that?
Okay, we didn't study the case of error on data collection, but what I think is worth to mention is that I didn't specify it for time reason, but I can say it now. Here, the data set have been collected with two different devices. So here, those data set up to primary school have been collected using this social badge. While for the university, the data has been collected using the Bluetooth technology that has much more error. And even if even if the underlying technology to collect data are different, we can still achieve what we expect. And I think that the error is pruned in the phase in which we apply basically the okay, in this phase here, I think you are removing a lot of noise in a sense that okay, up to now I'm mining motifs, but here I'm generating a null model starting from the original network. And in our case, for instance, was the shuffling of the time dimension. So we are in some kind breaking down the temporal correlation. And here, I think there is the part in which you are removing some noise. I don't know if it makes any sense.
Yeah, well, again, first of all, thanks for the presentation. It was rather clear. I have a couple of comments, questions about, in a sense, applicability and the limitations. I see two kind of limitations in the approach. One is related to the need for exact matches, okay, in the neighborhood, and the other one, of course, is the lack of second interactions, no? Yeah. So I was wondering, on the one hand, where do you think that these limitations do not, are harmless? So, in which, what is the setting in which this is not a problem? And on the other hand, if you have ideas on how to write partially.
Well, the idea to extend egocentric temporal neighborhood to something that is not exact, but using some kind of similarity among sequences, direction, and also the idea of extend it maybe to higher order graphs, or I expect that in some sense one could extend the first order with some kind of heuristics, losing a little bit, losing on exactness, but you can still add another order of information. You have to keep track of what is happening here in the second order. You have you have to think a way to probably an heuristic to collect this information into a string, but yeah, it's still an open work.
Okay.
Any other question from the public?
Sorry, I have a curiosity about the structures and the patterns that you use to build the embeddings. Are all the possible motifs that you can build with the one-hook neighborhood, or are some selected and captured motifs that
No, no, exactly. I mean, basically, when you have mined all the substructure, what you do basically is to apply the same statistical test done when motifs were developed. So you filter out many of them, many. And yeah, there are also in our study we show we've seen that the most important test that rise a lot of, that select motifs is the minimum frequency. What does it mean? It means that maybe we do not neither need a null model, maybe, and also you can do it in a incremental manner. So I can start with length 2, then length 3, and 4. Only if the motif is statistically significant, you can extend it. Because it seems that only the minimum frequency is the one that allow you to filter. Yeah, so for instance, when I show this picture, I do not remember in memory the size of the embedding here, the embedding we used. But in the paper, we show that only with 3 of these, you can compute basically obtain the same results. So in comparison with all the possible motifs, egocentric temporal motifs, we use only few of them.
This might also suggest that in this kind of applications, I mean, if the only thing that matters are the extremely well preserved motifs, then maybe knowledge is not really that important. So it doesn't really matter whether you screw out the other motifs, these 3 are enough. Right?
Yeah, yeah. But I also think it's related to the underlying data set. Like maybe those 3 motifs we found to be important for social context are totally different for, I don't know, biological setting or communication stuff or.
Yeah, I suppose what I'm saying is that in this particular case, your data is quote unquote multi-sparse. 3 are enough to describe most of it for your goals, of course. Yes. In other data sets where you don't have this property, and a lot of motifs really matter, and there aren't really clear winners, right? Yeah. In that case, knowledge might have more influence.
Yeah. Thank you. I think we can close here. Okay, no, sorry.
Like last question. When we're talking about the generation of the signature, given a temporal graph, or let's say given a motif or not node, I was wondering, I think it is, but it's some kind of really related to graph isomorphism as a problem, which I suppose that it is like, it should be like in P, right? It should be like polynomially, there should be an existent algorithm that can do it in polynomial time. And I was wondering, like, does the signatures are really like distinct? Yep. I mean, or is it like, is there a way like to generate 2 graphs with the which have the same signature but actually they're different, or why this is not possible?
Well, we prove in the paper that this construction allow you, since you are giving, well, let me first say that one of the biggest problems to graph isomorphism is related to ordering invariant. In a sense that if I would have an ordering, a given ordering for each node, okay, for me it's sufficient to compare nodes, okay, to edges, but it wouldn't be NP-complete.
Okay.
But since we are giving this ordering, we solve this problem.
Okay.
But wait, we are not solving the isomorphism problem.
Okay.
Of course. But what we are solving is because we can do this because we are looking only to the first neighborhood.
Okay, I see.
If we would like to go to the second order, it wouldn't
hold anymore.
Yeah.
I see. And just like last question, how do you like order the variables on this? Like, is a banner encoding that, or you are?
Yeah, it's a binary encoding.
Yeah, something very small. Okay. Yeah. Since you're explaining to Giovanni the response to his question, so basically it's true that when you are obtaining this signature, you are also not considering the difference between the nodes. Because the graph you showed, for example, they are the same graph, but the positioning of nodes are different, right?
Yeah, but let me say this A as a index of the node
Yeah.
is different from a label or a list of labels of a list of property. And encode the information of the list of properties. It's different from, okay.
So what
No, for instance, okay, sorry. They are identical because there exists a function that maps this ID that I use name into the second one. For instance, if I would change B with A, okay, this became this. If I would change C with D, this became this.
But there are two different nodes, right?
Yeah.
Ah, okay, okay. But the E that you take as the center of your graphs is identical, or not even the E?
No, it's identical. Yeah.
E is identical.
He
The
is-
occurrence of neighbors may or may not be identical.
Yeah.
I see. Thank you.
Okay. Thank you. And of course, we will put this on YouTube as usual. And now we are going to have a drinking bottle.
What time is it?
We also have a t-shirt, think and drink. And join us. You are more than welcome.
If you have like question that you want to like give in a more unstructured environment, then the last
After some
after
years.
like 20 minutes, then it might be the best option.
As usual, if you missed some part of the presentation or you want to watch it again, the recording will be available in the next days.
Thank you very much.
And okay, thank you very much to everyone. Next speaker will be Lotito, he is here, and he is going to talk about eigenvalue graphs and motifs in eigenvalue graphs. So related.
Thank you, looking forward.